we will study that what is the behavior of the fluidized bed in increasing and decreasing superficial velocity. So, it is our 18th class on the transport phenomena. We will study today the fluidized beds. By definition, the fluidized bed, it is a packed bed through which fluid flows with high velocity so that bed gets loosened and behaves as if it is a fluid, So, it implies that depending upon the requirement, the bed can be transported, like a fluid, in the fluidized state. Okay. Flow of liquid and gas can be imposed to get such a bed situation. Okay. Next thing is, why fluidization is required? Does it merely require for transporting from one place to other or something other? So, we must have the idea or the advantages, engineering advantages behind the creation of the fluidized bed. So, the next question arises that why fluidization? Why fluidization? Why this fluidization is required, and what are the characteristics of such fluidized bed? These are the two questions generally come to our mind. So, the why fluidization? This agitation of solid in contact with fluid causes, number A, an excellent contact between the solid and the fluid, between the solid and the fluid, because you are creating the agitation. So, every part of the particle as well as fluid will get intermixed with each other in a very effective manner. So, excellent contact happens. Number 2, an excellent contact between the wall, an excellent contact between the reactor wall and solid is possible. These two things gives rise to the beneficial effects extracted through the agitation process during the fluidization. So, these two excellent type of contact which can be developed, that gives rise to a situation where a uniform temperature even in the cases of highly exothermic reactions, can be maintained with a reasonable ease, Okay. The process is useful in industrial practices such as catalytic cracking of petroleum, catalytic cracking of petroleum, gas solid reactions. As I have given you the example in the previous class, gas solid reactions of metallurgical importance. There are so many gas solid reactions of metallurgical importances are there, and a uniform temperature can be maintained in those processes, in those reactions, by the virtue of this fluidization technique. And also this type of technique is of immense importance so far as the drying of ores by the fluidized bed processes is concerned. Now come to the behavior or characteristic of such beds. behavior of fluidized bed. In this characterization part of the fluidized bed, we will try to understand this fluidized bed characteristics by the virtue of two types of graphical analysis side by side. Characteristics of or behavior of fluidized beds. Let us suppose I am considering a graph here which is drawn between the superficial velocity along the x-axis. This is superficial velocity, generally that will be abbreviated as SFV for time being, that is plotted along the x-axis, and along the y-axis we are putting the value of pressure drop abbreviated as PD, and in the second portion of this blackboard I am utilizing a curve which is drawn between the superficial velocity along the x-axis, with the bed height along the y-axis. This is called the bed height or height of the bed. So, the variation can be seen here. Starting from this point 0, that is the O, increase the superficial velocity, you will find there is increase in the pressure drop. This increase, after that will have a tendency to attain a constant value of pressure drop. After some time the pressure drop will be constant. So, curve point A, this is another point B, and this is the vertical line drawn parallel to the pressure drop line. After that this point C comes, further increase, you will attain the point D, and in the reverse loop, if the superficial velocity starts to decrease, then in the back mode you will find that the superficial velocity decreases, due to which the pressure drop will decrease, but it will follow some another pathway as denoted by the curve DCE, right. On the contrary, if I would like to study now, this point, it is called, this is the fluidized state. So, this is called the minimum fluidization velocity. This is called the minimum fluidization velocity, abbreviated as VF. In the second diagram, we have an intention to study the change in the bed height as we start to increase the superficial velocity from 0 to maximum. So, in that case, you will find, let us suppose this is your superficial velocity at which this fluidization, minimum fluidization velocity is occurring. So, let us suppose this is the corresponding point. So, this point here also, this is called your minimum fluidization velocity. And if you have an intention to study the bed height, you will find that this type of graphical here, let it be point number A, this is the point number B, this is the point number B, this is the point number C, this is the point number C, this is D. In a direction of decreasing the superficial velocity, the curve will follow, the graph will follow this pathway up to this point. After that, we will find that this curve runs, the straight line runs parallel to the superficial velocity line. So, now let us try to extract the points which can be obtained regarding the behavior of the fluidized bed in the direction of increasing the superficial velocity, and again in the direction of decrease in the superficial velocity through the point of fluidization. So, because of the fact at this point the bed is going to be fluidized, so this is also called the upward fluidization velocity. So, number A, when the upward fluidization velocity increases from 0 past the point of fluidization, Let us try to extract what are the different points which can be extracted from this diagram. So, number one, when there is no flow, this point, so the pressure drop is equal to 0. It means, now corresponding to the second diagram, what inference can be drawn? That bed has a certain height, bed height has a fixed value. That means the bed height, the BH, has a fixed value, right? The first point which can be extracted from there. The second one, along the path A, B, C, D, along the path A, B, C, D, as one proceeds in the direction of increasing superficial velocity, as one proceeds in the direction of increase in the superficial velocity, what will happen? What will happen? The pressure drop increases. Imply that pressure drop increases. With the condition that the bed height remains constant, that means up to this point. Up to this point, the bed height remains constant. Okay, PD increases first with bed height equal to constant. That constant value that will equal to the fixed value as extracted through point number 1 has a fixed value also. The pressure drop that will be a function of velocity as per the Argun equation. As per the Argun equation for this region. Okay. Number 3, as the point B is reached, as point B is reached, as the point B is reached, you can easily see once you arrive at the point B, this is no longer increasing by a large margin. This is no longer increasing by a large margin, or almost constant value of the pressure drop is there, almost constant, not constant fully, but there is not so much increase. On the contrary, you can see a sudden increase in the bed height is there. A sudden increase in the bed height is there, but at the very same time, there is not much increase in the pressure drop. So, as point B is reached, bed height starts to increase, whereas pressure drop doesn't increase with increasing superficial velocity. That means even at the point number B, in spite of the fact that you have utilized whatever the value of the superficial velocity possible in that region, the pressure drop doesn't increase, but bed height starts to decrease rapidly. This happens when net weight of the bed, it will happen when net weight of bed that should be equal to upward force exerted by the fluid on the particles. That means particles start to float. That implies that means particles start to float in fluid get separated from each other and the phenomenon and phenomenon is called as fluidization. This phenomenon is called as fluidization, right? So this is a point which is denoted. This point is denoted at a point where the net weight of bed is exactly equal to the force exerted by the fluid on the particles, and this is the point where these forces are exactly balancing each other. That means this is a situation where the bed is just about to get fluidized. So in a technical term, in industrial practices, it is what is known as the onset of fluidization. So the next point is that is the point number 4 here. When superficial velocity increases further, then pressure drop is equal to constant, but bed height still increases. So it is possible that particles may be carried out with fluid at exit. This is attributed to the fact that the settling velocity of the particles, that means the velocity through which the particle has a tendency to get settled at the bottom, that is as per the Stokes law of the viscosity. So that settling velocity is much larger than the superficial velocity. This is attributed to the fact that the settling velocity of particles is much larger than the superficial velocity. Now the case number B, if superficial velocity starts to decrease from maxima to 0, that is, now we will try to understand the nature of the curve DCE. Okay. That is behavior of bed follows the curve DCE. Okay. So point number 1 which can be extracted here is pressure drop is equal to fixed. Pressure drop is equal to fixed when bed settles down settles down and begins to decrease once the point B begins to decrease. So the PD is equal to fixed, that means the potential the pressure drop is fixed, so that begins to decrease. Point C is reached first. Point C is reached during its back travel. Once the point B is reached, still the bed height doesn't decrease. Bed height doesn't decrease. Further, whereas pressure drop follows the curve DCE, where follows the curve DCE. What does it mean? It means that during the returning loop, this region BC is not achieved. That means the crossing the point of fluidization, the pressure drop starts to decrease. Follows the curve DCE. Or better to say, since the point C is reached, better to say it, write it CEO, the curve CEO. Okay, better to write CEO, more meaningful. Number 2, a bed of particles left alone for a sufficient time becomes consolidated but loosened when gets fluidized. It means bed settles down in a loosely packed fashion when a bed settles itself in a state of loosely packed. It means the bed height in the returning loop will have a larger value. Packed fashion, it means packed fashion during the time after fluidization, that means the point number C, after the fluidization, it means bed height is of higher magnitude but of constant value in the returning loop. This is all about the characterization. If the experiment is repeated, number 3, if the experiment is repeated by increasing superficial velocity from zero value set of curve ECD in the both the direction, ECD will be followed in both the directions and velocity at point C is termed as minimum fluidization velocity, abbreviated by the letter V suffix f, termed as minimum fluidization velocity. This is represented by letter Vf. Okay. So our next task is how to calculate this Vf. By utilizing the principle that the net weight of bed that should be equal to the upward force exerted by the fluid on the particles. So our next task is the calculation of Vf. The condition is net weight of the bed that should be equal to upward force. So the upward force exerted on the bed, that should be equal to pressure drop into the cross section area CSA, that is equal to delta P into A. Let it be question number 1. If L is the bed height at this point, okay, and epsilon is the voidage, then now the volume of the bed or the volume of the particles from which bed have been formed, that will be equal to 1 minus epsilon into A into the length. Okay. So the net weight of bed that will be equal to how much? The volume 1 minus epsilon into A into L into the density difference of the particle minus density of the fluid, rho P minus rho F into G. अब 10 मिनट के बाद. So this net weight of bed is equal to 1 minus epsilon into A into L into rho P minus rho F into G. So let it be equation number 2. Rho P and rho F are the densities of particle and fluid. So equating equation number 1 and 2, equating equations 1 and 2, equating 1 and 2, so that the delta P into A value, that should be equal to 1 minus epsilon into A into L into rho P minus rho F into G. So the value of delta P comes as 1 minus epsilon into L into G into rho P minus rho F. Let it be question number 3. So the expression for VAF, that is the minimum fluidization velocity, that should be equal to velocity as at the pressure drop as per equation number 3. That means you have to obtain the expression for the velocity utilizing the Argun equation by putting the value delta P, that is equal to 1 minus epsilon into A into L into G into rho P minus rho F. For a bed containing smaller particles, with equivalent diameter is less than or equal to 0.1 mm, because of the fact that the diameter has a great role to play in order to decide the Reynolds number, which is nothing but it is ratio of inertial to viscous force. So this dP is less than 0.1 mm, it means the Reynolds number is lesser than or equal to 10, and Vf is given as Vf is equal to rho P minus rho F into G into dP square divided by 150 mu into epsilon cube divided by 1 minus epsilon. This is equation number 4. This is called the Kozni-Karman equation. This is called Kozni-Karman equation for the onset of fluidization. This is called Kozni-Karman equation for the onset of fluidization. However, if you consider in the larger particles in the bed, that is the value of dP is greater than or equal to 1 mm, that means for larger particles dP is greater than 1 mm, Once this happens, then the inertial forces are more dominant. That means the value of Reynolds number is increasing. If the value of Reynolds number is increasing, that means the ratio, that is inertial force divided by viscous force, that means inertial force is increasing. This is the possibility under which the Reynolds number can increase, because of the fact the viscosity of the system viscosity in the present situation cannot be altered. So, the only thing that the inertial force can be altered. If it can be increased by having a larger volume equivalent diameter, then the inertial force may be increased. So, here if I am considering that the larger particle with dp is greater than 1 mm, it means inertial forces are dominant. Inertial forces are dominant. So, in this case Vf can be determined by using the full Argun equation, Now, utilizing the Stokes law, expression for settling velocity, Vs comes as small Vs comes as rho p minus rho f into g dp square divided by 18 mu divided by 18 mu. Let it be equation number 5. Now, dividing equation number 4 by 5, so doing equation 4 by equation 5, equation 4 by the Korzeny-Karman equation. So, equation 4 by equation 5, if you divide these two equations, you will get Vf by Vs, that should be equal to 3 epsilon cube divided by 25 into 1 minus epsilon. Let it be question number 6. Here, if the bed void is lying between the value 0.4 and 0.5, so the ratio of settling velocity to the minimum fluidization velocity will be greater than 50 but lesser than 78. So, utilizing this concept, an important a very renowned chemical engineer McCabe suggested that a fluidized bed this is the industrially drawn conclusion by this chemical engineer, that a fluidized bed can be operated at velocities as high as 30 Vf and occasionally at 100 Vf. Since all the particles may not have same size and shape, as well as dp is only an average value, and dP is only an average value, that is the statistical value that you have obtained, average value. So, fine particles may be carried out with the fluid at the exit, This phenomena is what is called as illustration, carried out with the fluid at the exit. This completes your fluidized bed and packed bed and its characteristics which is needed for a metallurgist. In the next class, which will be the last class of the transport phenomena, is the momentum transfer of the that means this section of the transport phenomena. In that class, we will discuss the characteristics of turbulent flow, the utilization of the Prandtl mixed length model to evaluate the Reynolds stresses and to provide an explanation for the momentum transfer. So, we will meet in the next class for the ending of this part of the transport phenomena. Thank you.